Welcome to this presentation on quantum numbers. Quantum numbers are essential tools in understanding the behavior and placement of electrons within an atom. These numbers help us describe the unique quantum state of electrons, providing insights into their energy levels, orbital shapes, orientations, and spin directions. By the end of this presentation, you'll have a clear understanding of the four types of quantum numbers and their significance in atomic structure. Quantum numbers are like a unique address for each electron in an atom. They help us locate and understand an electron's position and behavior. These numbers are crucial for explaining why elements behave differently and how electrons distribute themselves in an atom's orbitals. Each of the four quantum numbers contributes specific information about an electron's properties. The principal quantum number, symbolized as n, identifies the primary energy level or shell of an electron. This number starts at 1 and increases in whole numbers, where larger values indicate orbitals with higher energy and size. For example, when n equals 1, the electron resides in the K-shell, the lowest energy level. The total number of orbitals within a shell is found by squaring the value of n. Furthermore, you can calculate the maximum number of electrons in a shell by multiplying 2 by the square of n. Examples, using the formula 2n squared. K-shell can contain 2 electrons. L-shell contain 8 electrons. M-shell contain 18 electrons. The Azimuthal quantum number, represented as L, provides details about the shape of an orbital and divides the main energy levels into subshells. Its values range from 0 to n-1. For example, when n equals 2, I can take on the values of 0 and 1. Subshells are designated based on their L values, such as S, P, D, and F, each with unique shapes and energy characteristics. The magnetic quantum number, symbolized as ML, is a critical component of quantum mechanics as it defines the orientation of an orbital in three-dimensional space relative to an external magnetic field. For any given subshell, ML values range from the negative of the azimuthal quantum number, L, through 0 to the positive value of L. The total number of ML values corresponds to the total number of orbitals in that subshell, which is given by the formula 2L plus 1. For example, in the S subshell, where L equals 0, there is only one possible ML value, 0, corresponding to a single s orbital. In the P subshell, where L equals 1, ML can be negative 1, 0, or positive 1. These values indicate the presence of 3 p orbitals, which are named based on their orientation as px, py, and pz. In the D subshell, where L equals 2, the possible ML values are negative 2, negative 1, 0, positive 1, and positive 2. This gives rise to 5 orbitals, each with distinct spatial orientations. Finally, in the F subshell, where L equals 3, the ML values range from negative 3 to positive 3, including 0, resulting in 7 orbitals with even more complex shapes and orientations. The magnetic quantum number provides a deeper understanding of how orbitals are arranged and how electrons occupy these orbitals, particularly in the presence of magnetic fields. The spin quantum number, written as ms, provides information about the spin direction of an electron within an orbital. Electrons can spin in one of 2 directions: spin up, represented by positive 1/2, or spin down, represented by negative 1/2. This quantum number is crucial because it ensures that no 2 electrons in the same atom share the exact same quantum state, adhering to the Pauli exclusion principle. This diagram visually represents the hierarchical structure of electron organization within an atom, as determined by quantum numbers. The outermost teal oval symbolizes a shell, which corresponds to the principal quantum number, denoted as n. For example, the second shell is the L shell, where n equals 2. Shells are energy levels containing subshells, and the number of subshells in a shell is equal to n. Within the shell, the red boxes highlight the subshells, which are defined by the azimuthal quantum number, L. The L value determines the shape of the subshell. For example, the S subshell has L equal to 0, and its shape is spherical, as shown in the leftmost part of the diagram. The P subshell, where L equals 1, is represented by 3 separate orbitals oriented along the x, y, and z axes. These orbitals resemble dumbbells, indicating their unique spatial orientations. Lastly, within each subshell, there are orbitals, depicted as the individual shapes within the red boxes. Each orbital is defined by the magnetic quantum number, ml, which specifies its orientation in three-dimensional space. For the s subshell, there is only one orbital as ml equals 0. For the p subshell, there are 3 orbitals corresponding to ml values of -1, 0, and +1. These orbitals are labeled as px, py, and pz. The organization of shells, subshells, and orbitals is essential for understanding how electrons are arranged in an atom and how they interact with magnetic fields, external energy, or neighboring atoms. The Aufbau principle is a fundamental concept in chemistry that guides how electrons are arranged in an atom. The term Aufbau comes from the German word meaning building up. The principle helps us understand that electrons fill the lowest energy orbitals first before moving to higher energy levels. Using the diagram provided, the arrows guide the sequence of subshell filling. For instance, the 1's orbital, being the lowest in energy, is filled first. After that, electrons move to the 2's orbital, then 2p, and so on, as indicated by the diagonal arrows. Let's take some examples. For hydrogen, which has just 1 electron, the electron goes into the 1's orbital, resulting in the configuration 1s superscript 1. For oxygen, with 8 electrons, we follow the sequence: 2 electrons in 1s, 1s superscript 2, 2 in 2s, 2s superscript 2, and the remaining 4 in 2p, 2p, giving a configuration of 1s superscript 2, 2s superscript 2, 2p. A more complex example is iron with 26 electrons. Using the diagram, we fill the orbitals as follows: 1s superscript 2, 2s superscript 2, 2p, 3s superscript 2, 3p, 4s superscript 2, 3d. This principle not only provides a method for writing electronic configurations, but also helps us understand the chemical properties of elements based on their electron arrangement. In conclusion, quantum numbers provide a comprehensive framework for understanding the unique states of electrons in an atom. They define the energy level, shape, orientation, and spin of orbitals, helping us predict electron behavior and chemical properties. Mastering these concepts is fundamental to exploring atomic theory and quantum mechanics. Thanks for watching. To deepen your understanding of SI units, explore our comprehensive resources, including revision notes, past questions, gamified quizzes, and workbooks. These tools are designed to help you master the concepts effectively and enjoyably,